I'm Anima Anandkumar. I'm professor at Caltech, and here with me is Arvind Krishna, CEO and chairman of IBM. Thank you.
Anima, it's a real pleasure to be here. As you said, World Government Summit has paid attention to AI, I think, right from the very beginning, and that's why it's so exciting to be here. It's also so exciting to see the progress within the nation on AI being deployed in so many different initiatives across both private industry and public.
Absolutely. I was here just several months ago in Abu Dhabi to have a summit on energy and AI. And in this region, there's a lot of leadership in terms of asking, how can we have clean sources of energy for AI? How do we have sustainable development of AI from natural gas, nuclear, to harnessing AI also for energy, right? How do we derive AI for clean sources of energy? And we'll get through all of that. But before that, maybe we want to start with a bit of history of how AI has come along. Modern AI, if you look at it from 2010, it started with the ImageNet moment where we had the internet with lots of data, and ImageNet data set was collected with labels. So what are in the images along with the examples of those images. And neural networks for the first time were able to beat other methods. And that led to rapid progress in computer vision. And we've seen that working in the real world, from face recognition in the airports to on your phone. But the language models have almost were a big surprise to the whole world when ChatGPT was released more than 2 years ago. And but for those of us who are in the field, who've been working in AI, you could see that come all along. So several years I spent at NVIDIA until recently, where we led many of the development of large-scale AI for language models. We open sourced the code. We had OpenAI and others build on it. And AI has really been this open source revolution where a lot of the development has been shared together with the community. And recently, many of you have seen the DeepSeek moment, right? So DeepSeek released these models also as open source. There was a lot of confusion, maybe a lot of misinterpretation of what that means. Personally, for me, I believe it's a great success of that open source and a natural evolution of people building on each other's work and improving, because DeepSeek built on Meta's Llama models, further developed, innovated in terms of what would be good, efficient architectures, what would be good combination of algorithmic techniques, and brought that together and released it. And now everybody, including IBM, I believe, are using these models and further developing on that.
Yeah. So maybe one thing to add. Yeah. I think a massive advantage, building on the work that not just NVIDIA but others did, and in a shared way, is we got away from label data. You're right. ImageNet was absolutely the moment between 2010 and 12, but that required a lot of human work in addition to computing work. Yeah. And then around 2020, I'll say maybe going back to 2017, people came up with these techniques of just using a lot of data and letting the machine question itself to make it simple of getting to the right answer. And that has proven to be incredibly successful. That means you don't need those armies of people in the background labeling data. And I think that was a huge progress on language. And languages underlies a lot of human cognition, a lot of human processes. And that was, I think, incredibly important as a moment. And to the point you're making, now it's feeding on each other. The transformer world did something, academics did something, another company does something. Going all the way, I think DeepSeek is just actually a moment along this path. It's not the end, and it's not a unique inflection.
Yeah, I believe so, and thank you for clarifying that. In fact, language models are what we call generative AI, right? Meaning, rather than just predicting on a given task, like, for instance, classify what's in an image, you're generating entire pieces of text or generating images as well, could be multimodal generation. And that really was also a revolution because you went away from human annotated data to just training on internet scale data, right? And when we have such massive data sets in the internet, that also brings forth the requirement for large scale compute in what we call the pre-training stage, but also now after training, having to align the models and what we call test time scaling at test time, having the model more capability to think and then answer has proven to be very effective with reasoning.
Yeah. Look, the ability to read and to follow all human language, language is not just a language, be it English, be it Arabic, be it French. Language also, for those who write scientific papers, is a unique structure to that language. For those who do chemistry, is a unique structure. If you look at financial regulators, they have that unique structure. So whether we use the term grammar or algebra or language, there is a massive variety. So the ability to do that, to do reading, and to be able to generate, and to be able to, at one level, let's think about it as it's reading at least a high school level. Suddenly a lot more tasks become within at least imaginable that previously you could think about. Certainly, facial recognition is important. Airport, to the point Anima made, getting through an airport is so much quicker than when you could not do facial recognition. Being able to classify images, whether for insurance purposes and so on, is really useful. But I think the use cases explode into the thousands and millions once one can read and add that capability and do it in a way that is unique to each enterprise, each government, each department. That is really something which everybody's imagination should start thinking about. How does one leverage these technologies in all of those examples?
Yeah, absolutely. While it's fun to play with chatbots to create new jokes or new poetry, there's a lot of deep, impactful use cases, right? And that's where in this event as well, there's a lot of conversation of what kind of jobs will this affect, where will this be human in the loop versus fully autonomous agents, right? So we're going from just language models being in isolation to using that in the loop with other tools. You can book tickets, you can go reserve in restaurants, so all kinds of tasks could be automated using the understanding of the language, but also going and executing various tasks. And this is what we call them as agents. And in fact, one of the first work that was done with AI agents was when I was at NVIDIA. My team showed how when ChatGPT was just released more than 2 years ago, you can use that to play Minecraft, right? I don't know how many in the room have played that, but the idea is instead of just going to completing one goal, you can explore the environment. You can mine for diamonds, you can build a structure. So that complexity of variety of tasks that are out there where you need to go explore. You don't just go finish one goal, but you go and explore what is interesting in an environment. We were able to show that with Minecraft, but of course now that has evolved into a lot of real world applications.
Maybe, Anima, I'm going to pull your leg a little bit. It's very interesting. Minecraft. So AI is a field that has gone through a few evolutions. It began, you can debate in the late 50s or early 60s. People actually thought neural nets was the answer. Then they backed off because the computing wasn't good enough, just to be straightforward. Then they went to alternate techniques and then they came back. In the 1960s, it is interesting, Minecraft was one of the first programs that actually IBM released as
I was not aware of that.
as an open source little piece that people could go run on first the mainframe and then what became Heathkits and the personal PC in the 70s. It is small, it is kind of manageable. Chess was out of reach in those days. Those came much like 10 or 20 years later. So it's interesting. We come back to the same things to prove a concept and then sort of generalize from there, I think.
Yeah. Wow, that's such a great story. I was not aware of that. So I'm curious at IBM now how you're thinking of harnessing the power of language models and agents, and what do you think are the kinds of applications and tasks that will be disrupted by this?
So we are very excited. As Anima laid out, we are very excited by the possibility of all of these. Our focus is very much on business to business as opposed to business to consumer. We think there's a large number of players out there in business to consumer, and I think that they will be very successful. Business to business adds a few, whether you want to call them restrictions or capabilities to what was being described. In a business, you also need to worry about how can I add private data. The example Enrique used just before, I think was like spot on. The likelihood you're going to take unreleased earnings from a public company and put them onto any public model is like zero. I mean, like it's not going to happen. If you also lay into it predictions for the future about your own company, every regulator would actually insist that you kind of keep that to yourself. So how do you add private data, if that's an example of private data, to a public model to make a much better narrative, to make a much better prediction, to make a much better speech? That's a whole area where we are investing very heavily. But then you begin to say, well, but you're not going to go run that on a 100,000 GPU cluster because that cost, the return is not there because the uses of that are going to be by a few people. Let's call it thousands, not billions. So how do you do things in a much more efficient way for that use case? You can begin with a very large base model, much like the DeepSeek example. They used Llama to teach. We don't quite know yet, I think, what they began to distill from. We'll find out eventually. Right. But they certainly used both Llama and maybe others, but I'll leave that to the courts to decide. We'll go to what they claimed publicly. Right. But you begin to use a large base model that may have been invested in the hundreds of millions. But can you, with a couple of million, or with maybe a few 100,000, add some private data, and then ask the model to focus in on that private data to really begin to leverage that for either a narrative, that's a straightforward, that's, I'll call it the first layer, not a lot, but some value. But can you begin to go from there to say, can I add these other things and make predictions, call out differences, find moats? All those things is a great example. But even go wider than that. Somebody writing code, everybody has their own style of writing code. That style may be quite different than somebody else. It's not, in some sense, incredibly proprietary, but you probably don't want it to leak out to everybody else because it is an advantage for a place to know how and what their discipline is. And so how can you add that to a base code model so now it's unique to that enterprise? Or a documentation style. Or if you're in the finance industry, there is a regulator that is unique to each nation. How do you begin to add? I think this ability, part of which I'll call is enterprise-centric, is what we're very focused on. And the other part is going to be domain-centric. So today, the estimate on the first is 1% of enterprise data, 1%, has been in any way exploited by AI models. So that's a huge opportunity when you think about it. The other piece is, right now there's very few domain-specific models. Most models are very general and horizontal, very powerful, but that's only half the world. We believe that by 2027, 50% of all the models will have domain specificity.
Mm-hmm. Mm-hmm. Yeah, that makes a lot of sense. And we'll get to domain-specific models in a second, but before that, maybe coming back to these lots of potential applications, right, where language models are in the loop, but maybe you want them to be more trustworthy. For instance, hallucination is a problem that's getting better with the generation of models, but not fully gone. And so if you want some kind of guarantees of how these models will perform under various conditions, and maybe not completely in the wild, that's hard to do, right? But let's say in domains where it's about regioning, so you have a set of logical constructs, and so based on that, can you verify what these models are doing? And there's a lot of rich work, in fact, in classical AI, what we call formal reasoning, right? You start with axioms, and then you can verify every statement being made. And there's a rich history of formal programming, and there are languages like Lean, which can help prove theorems, but also verify every step. So that when we use language models in the loop with programs like Lean, which verify every step, we completely remove hallucination, but for those specific specific goals of proving mathematical theorems. And so I'm curious, more generally, can we bring these concepts? Because we open sourced what we call Lean Dojo, the first open source framework, bringing this together. And since then, there's been a whole range of developments. You see AI now being able to prove Olympiad level math problems, AI being able to come up with new kinds of circuits. So all these designs or statements that AI makes, if you want some kind of guarantee, you want some kind of verification, there are other tools that can come together, and that could also be very impactful for different businesses.
Look, to give you some intuition, to factorize a large number is an incredibly hard problem. Verifying, if you're given two factors that you can multiply them and get the correct answer, is easy. So the point Anima is making, there's a very large class of problems out there, by the way, not just in mathematics, even in other areas, where you can verify the answer. So she's saying, add those guardrails that you put in a little bit of verification, and that'll prove that you're not hallucinating at all. She mentioned chip design. Laying out a chip design is an incredibly hard problem. It's known you cannot actually maybe get to the eventually optimal answer. AI helps you get to a much better answer, you know that. Then that you're left with that niggling thought, what's happened if I designed the wrong circuit? It turns out verification is actually much more straightforward. So if AI suggests a design, you can verify it's correct. You may not be able to verify it's the most optimal, but you can verify it is correct. That gives you a lot of confidence in trying these things out. In question and answer even, you can verify that the answer is coming from a corpus as opposed to something else. And those become techniques that you should use. So as you begin to constrain perhaps the use cases, you can get verification up where you can get a lot more confidence. I think that that's an approach that when we talk about deployment techniques, everybody should begin to use for how you get value without kind of running into that, let's call it 10% risk of hallucination. Look, for a pure consumer thing, you're asking you to draw something. If it hallucinates, so what? It's kind of interesting, it's intriguing. But if you're in government and you're using AI to give a citizen answer, you probably don't want it to hallucinate.
Yes, absolutely. In these applications where AI is asked to reason and come up with answers that are, there's certain ground truth to it, right? You really want that to be accurate. But there are other applications where AI could be a friend. So speaking of domain-specific applications, we trained the first genome-scale language model. So think of instead of English or Arabic as the language, we use the language of life itself, which is genomes. So we took all the known bacteria and viral genomes, so everything that's recorded in the biobank, everything that's known to us, and trained a model and asked it to come up with new kinds of genomes of new viruses, like that was during the pandemic, and there be new variants of coronavirus, and we are prepared before they happen. Can we design new proteins? And there, hallucination could be our friend. And in fact, we've seen that recently in some of the really exciting experiments we are doing in a collaboration with Frances Arnold, who is Nobel Prize winner at Caltech for her work on directed evolution, on how to design new proteins. And so now you can use these genome-based language models as a new kind of design space for proteins, and we saw that it came up with new designs of proteins that were entirely unknown to humans. And it was entirely in a different part of space, and it was even better, had better activity, was thermally stable for an enzyme function that was not known before. And that shows the potential these models have for scientific discoveries.
I think these are great examples. A few of our clients, so many of you may be aware, there are these chemicals known as PFAS chemicals, kind of paraphrased as forever chemicals, and most places are outlawing them. They're forever because they don't actually disappear. The half-life is in actually thousands of years in the environment. They're very useful because they make things very inert, very stable. They're used in automobile, they're used in airlines, they're used in, by the way, cosmetics, because they keep the thing stable. One of our clients, L'Oreal, came to us and said, can we get a model that could substitute these with alternate chemicals that are there that are known to people but have similar properties. And all of a sudden you can begin to do, because actually it turns out organic chemistry has a lot of rules that you can bake into these models, and you can ask it, can you maybe find an alternate, maybe from the known library, or maybe you can suggest something to make and formulate, and that is turning out to be incredibly useful as we go forward. So we think in many, many areas, these domain-specific models that Anima spoke about, you have got to put in a little bit of, I'll call it domain comes with the word knowledge, so there is some knowledge that is known, yes. And you begin to insert that, and you can go forward. But you've been doing some work on inserting knowledge in, haven't you, on some of these models?
Yeah, thank you. Yeah, definitely. And that's kind of like coming back to what we can do with domain-specific knowledge, right? Because, we don't unfortunately have as much information in the internet for other kinds of data as compared to text data. And that's why the text models were the first ones to become so good at being able to kind of put all that together and come up with also new generations. And if you look at data, for instance, that is not discrete tokens, it's not like vocabulary that is fixed, whether it's in English or in genomes or in chemicals with a fixed set of atoms. Instead, if you think about the weather, that happens across the globe, right? And you can keep zooming in more and more. And in fact, if you think about how hurricanes and different extreme events happen, you may need to zoom in a lot, because looking at very fine scale information there is valuable to predict where the hurricane goes next. And so for these kinds of models, we know a lot from physics, right? We have some amount of data. We've collected data for the last 4 decades since the satellites were up there, and we made weather forecasting as a field that had this continued data collection. So we have some amount of data, but we also have the valuable knowledge of what the physics tells us. How does the fluid dynamics happen? How do, if you look at zooming in and out, the eye of the hurricane, how much is the movement there? So we can use the laws of physics to predict that, and combining both physics and data together, we created the first AI-based high-resolution weather model when I was at NVIDIA in collaboration with Caltech, Lawrence Berkeley Lab, and many other universities. And since then, AI-based weather models and climate models have really taken over the field in many ways. They are much faster. So what would take a big supercomputer that is CPU-based now can be run on a local desktop with just a single gaming GPU. So we open source the model. It's running in ECMWF, the premier weather agency. There's many others who are building on top of this, and including here in this region, I'm aware of a lot of work done on local weather forecasting, because it is critical for a lot of the events. And going from weather to climate, when we think about long-term climate and what climate change could bring along, and the ability to predict that is really important for us as a human race together. And so how do we use the power of AI to bring massive speed up? So we're talking about speed ups from tens of thousands of times to even more. And we need that because we need to get to these high resolution predictions in order to have confidence in being able to predict climate change and take corrective action.
But take what Anima said and slightly generalize it. So one, a lot of people struggle with really arcane and hard to understand mathematical concepts. You can go ahead and do optimization, and then you tend to hire the few people in the world, typically people with advanced degrees in physics, math, computer science, engineering, to come and do it, but that is kind of scale limited. If you can capture the knowledge implicit in those techniques in an AI model, but then begin to leverage it using much more natural language, it suddenly brings the ability to use those techniques to a lot more people. Combined with, here, 100 to 1,000 times less compute, that makes it much, much more affordable. That's kind of been the history of technology. You take something, it is very, very hard to do, you encapsulate it, you put a simple wrapper around it, you drop the cost, you drop the cost, you drop the cost, suddenly everybody can avail themselves of it, and the benefits spread to all of society and the entire economy. I really believe we're at the beginning point of that. Weather simply happened to be a great proof point, but I can imagine whether it's optimizing for risk, whether it's in farming, whether it's in irrigation, whether it's in how do we route logistics, so many problems which are more or less done sometimes by intuition and seat of the pants. I'll give you guys a shocking statistic. 30% of all containers in the world, when they go across the ocean, are empty. 30%. So think about the energy you can save if you can actually get to optimize that they're equally loaded in all directions. We know that's possible, but just because everybody's just worrying about their own container and like staying at the mini level, because that problem is so big, people don't want to tackle it. These are all examples of what we can do to benefit. This is like a benefit for everybody. It benefits the owner of it, it benefits society, it benefits sustainability. It's kind of across the board. And that's so many exciting opportunities, I think, as we open up these models.
Yeah, absolutely. And to me, that's why the next wave of what we'll see is what we call physical AI, right? Being able to understand the physical world in all its complexity, solving some of the hardest scientific challenges, like, can we make nuclear fusion possible and a reality? We've designed AI that can simulate and understand the complex hot plasma more than 1 million times faster than what was possible with traditional simulations. We've used AI to understand, can we sequester carbon dioxide underground and do this at very high resolution at multiple wells? And ultimately, we need techniques like these to tackle not only climate change, but bring in clean sources of energy. And to do that, AI is critical. So thank you so much, Arvind, and it's a pleasure to share the stage.
Thank you. You can see the excitement we have for what it's going to do for you. Hopefully that all excites and motivates all of you to do a little bit yourself. Thank you.
Thank you.